Welcome everyone. Solenoid is a finite number of continuous turns of conducting wires wound in a helical shape. And we have discussed magnetic field of a bar magnet is similar to that of solenoid. Hence, bar magnet can be assumed to be same as large number of current carrying loops placed adjacent to each other. Two faces of solenoid are similar to the poles of a bar magnet. The field lines lead from one face of the solenoid into the exterior, and hence this face is like a north pole of the magnet. Similarly, the field lines enter the solenoid at the other face, and hence the face is like south pole of the bar magnet. Now if a solenoid or a bar magnet, if it is cut into two, the bar magnet in perpendicular to length is cut into two, or the solenoid is cut into two perpendicular to the length, they are again two small parts, two smaller solenoids, two smaller bar magnets, and as their length is half, it is proportional to magnetic moment. Now in this video we are further explaining how a solenoid and our bar magnet are much more identical. Here we are going to find out the magnetic induction B on the axis of a solenoid. N is the number of turns per unit length, 2 is the length of the solenoid, A the radius, I the current through the solenoid. The solenoid is placed such that the axis is along x-axis of the coordinate system and the center coincides with the origin. Left end of the solenoid lies at the position minus L and right end at the position plus L. P be a point distance r from the center of the solenoid to the point P. To calculate the magnetic induction B at the point P on the axial line of the solenoid, consider a small element solenoid of thickness dx, the blue colored one, and the thickness dx is x distance from the center of the solenoid O. The distance of the point P from the small element dx of the solenoid is r minus x. As n is the number of turns per unit length, the number of turns in small element dx is n dx. We have learned in earlier section B is equal to mu 0 I a square by 2 into x square plus a square power 3 by 2 in the case of a current carrying circular loop, where we are taking x from the center of the loop. In this figure, that particular dx is at a distance r minus x from P. So instead of x, we write 2 into r minus x the whole square plus a square to the power 3 by 2. And in this figure, the equation 2r minus x the whole square plus a square raised to 3 by 2 is the denominator section. In that point, the value of x and a is much less compared to r, and the constants are mu 0, n, I are all constants. So total magnetic B can be calculated by dividing the total length of the solenoid into small elements, that is shown in different colors, dx different, and integrating between minus L to plus L. dB. dB is written the same manner. Again underline the denominators and the constants. I, A, N, mu 0 are constants. The values of x and a square are neglected because that is much less when compared to r. So, in the denominator, if you remove x and a square terms, the remaining will be b equal to mu 0 ni a square by 2 within the integral minus L to plus L dx divided by r cube. Hope it is clear. Now on integrating, integral here again r is a constant because the point P is at a finite distance. Now integrating, taking r cube outside, integral minus L to L dx. And integral dx is x. Giving the upper limit and lower limit as upper limit is L minus lower limit is minus L, you will get it as 2L. In that, multiply numerator and denominator by pi. We have studied in earlier sessions that pi a square is the area. Pi a square is the area vector. Area means area of loop. And 12 is the total length of the solenoid. And M is given as I into A. M is magnetic moment. Magnetic moment is defined as I into A. And A, I told you, it's the area of each loop. Area vector is taken as normal to this area A. It's very clear what is area capital A, and area vector is always defined as a normal perpendicular to the plane of A. And area A is for sure pi a square. If you could look at that, in the numerator, all those things other than mu 0 by 2 pi is M. And in the denominator you have r cube. So it will be b is equal to mu 0 by 2 pi into the remaining is m by r cube. If you could multiply numerator and denominator by 2, you will have mu 0 by 4 pi into 2m by r cube. The equation is exactly the same as the magnetic induction on the axial line of a bar magnet. So the equations clearly makes us understand a bar magnet is equivalent to a solenoid and the magnetic field lines are the same. Thank you.